OK， 好，各位啊，感谢大家光临啊，今天各位感谢大家光临啊，今天呢很荣幸啊，今天是我们 TNT 大讲堂的第2季的第2讲，今天众筹请了一个大咖来讲座，我前面讲过了，这也是良师益友啊，就跟我们合作很多年，已经在这个 Slicer 的研发和这个应用上，我们做了很多的合作。这是来自于哈佛大学一些SPRCS 叫 Physical Planning Laboratory， 就是外科计划实验室的 rkikinis3dsliceroverviewlecture2019教授。那么他是最早提出在全球最早提出来说要研发这么一个通用平台的医学理软件的人啊。那么我们这个尊称他叫做3D slicer 之父啊，在座的很多同志对 slicer 都很熟悉了，所以今天我们有幸请到他。大家等会儿呢就因为图文并茂，还是比较理解啊。听完以后如果有问题，不用客气啊，有什么问题在课后的讨论环节可以提出来，打中文也行，打英文也行啊。如果中文的话呢，可以看到以后会给这个 Kikinis 教授翻译出来，然后他的回答我再翻译成中文给听，好吧？所以今天大家不要有压力，但是还是努力听讲啊，听母语啊。那么下面我们就有请Kikinis 教授来做讲座。Now please welcome Professor rkikinis, please.
Thank you, Dr. Chen. I'm very happy to be here, not in person, but at least virtually. And I'm looking forward to give you some evening entertainment and to tell you about some of the background in 3D Slicer. The picture that you see on my cover slide is a picture of Boston, an aerial view. We see the Charles River on the left, we see the baseball stadium, Fenway Park at the bottom right. However, right now I'm actually not in Boston, but in Germany, in a city called Bremen. And so I'm talking to you from Bremen. Now we have a technical problem. Here we go. So I'll talk to you a little bit about kind of the history of how we got to where we are today. Then I'll give you a little bit of background about the problems that we are trying to address with 3D Slicer, and briefly cover some of the upcoming technologies that we are investigating to improve Slicer in the future. I like to begin my presentations with basically acknowledging that all the work that I'm doing is based on the vision of my mentor, Ferenc Zsoles, who died a few years ago, but whose vision continues to carry us forward. It's also the case that most of the work that I'm talking to you about was actually paid for by the NIH, the American National Institutes of Health, because there is a vision there at NIH to make scientific data accessible and usable to scientists from all over the world. And this has been formulated on a policy level and in turn has been turned into funding opportunities for people who want to work on this type of technologies. 3D Slicer basically exists for quite a while. We started 3D Slicer started as a master's thesis. It was the master's thesis of David Gehring, who was working with Arya Nabavi, who was a neurosurgery fellow in the first generation interventional MRI that we had at the Brigham in the early 90s. The lead neurosurgeon for this project was Dr. Peter Black. And as I mentioned, the vision of 3D Slicer came out of the vision for image-guided therapy that my mentor Ferenc Joles developed. David wrote his master's thesis doing work inside this double donut configuration MRI scanner that allowed to do surgery and imaging without having to move the patient. Since then, we have continued to develop the technology, upgrade, added features and capabilities. But keep in mind that 3D Slicer really started as an interventional tool from the beginning, from day one. Today, fast forward a quarter century later, it's an open source, community-based software. Community-based means that both the application engineering and the core engineering is done by a community, not just by a single lab, but really contributions from many different places. The core engineering team includes people from Canada and a variety of locations inside the United States, and now beginning also participation from Europe. The Slicer community is open to anybody who wants to come and participate. So there is no application process. You can just say, I would like to participate, and you can do that. And accordingly, it's very easy if you are willing to do it. So what kind of problems are we addressing with 3D Slicer? The fundamental problem in image-guided therapy is that we would like to use non-invasive imaging as a way to augment what the eye sees and to help the interventionalists or surgeons with devices, whether they are robots or tracking systems, and to be able to do an update of the preoperative images during a procedure. The purpose of all of this is to, on one hand, reduction of invasiveness, but on the other hand, also helping to improve the quality of the work. So the tools that have found their way into 3D Slicer include a variety of classes of tools, such as segmentation, registration, volume rendering, and a number of other techniques like diffusion tensor imaging, tractography, and dynamic analysis of time series data. These are just examples of the core technologies that you find in Slicer today. This development is further driven by the fact that we have an increasing number of data sources from a variety of different methods that let us look into the body. Besides MRI and CT and other forms of X-rays, I just would like to mention PET-CT, of course, different forms of ultrasound. And then finally, we can drive some of these scanners in ways that allow us to extract information through analysis of time series or of a series of other dimensions that give us more information, more detailed and specific information about what's visible. One price that we pay for these increased capabilities is that the complexity required in order to analyze the data is increasing. I'm using here two examples that are most likely familiar to most of you, which is functional MRI and diffusion MRI. In both those modalities, which are specialized versions of magnetic resonance imaging, the acquisitions are combined in a variety of different ways and result in very complex data, which in turn need to be analyzed by sophisticated post-processing in order to provide meaningful information. So medical image computing, abbreviated MIC, is of increasing importance, and it is more important because there are more applications that require MIC processing, and the data is both more complex and just plain more data. And so, you know, if I think back a quarter century ago, a CT acquisition might have been 60 megabytes of data. Today, you do an fMRI or a diffusion MRI acquisition, and it's easily a few gigabytes of data, so 3 orders of magnitude more data. And we need complex post-processing to find the clinically important information in that data. So Slicer is essentially a MIC tool, a medical image computing tool that is intended for research. We have not applied for clinical use, and so if you use Slicer in the clinic, you have to make sure that you are in compliance with local regulations, and often that means that you do it under a research protocol. Every country has different rules, so if you choose to go that direction, you have to make sure we don't make any guarantees. We just tell you, you can have it as is, you can do whatever you want, but you are responsible for it. So what we do in our clinic when we use Slicer as a research tool is that we always make sure that we do calibration and careful adjustment as necessary to make sure that the software performs with the data exactly as we want it to perform. The software is open source, and because it is open source, if you have access to people with a computer science background, you can add functionality to it. And we have an app store where people can choose, but it's just their choice. It's not a requirement to make some of these extensions available to other people. So again, you can use it in any way you want. It is free, it is open source. You can extend it. You can keep all of it for yourself, or you can share with other people. It's your decision. We don't force you to do it one way or another. But we are trying to make it easy to install and use Slicer. So we have invested, and I'll talk a little bit later about it, a significant amount of engineering resources to turn Slicer into something that you can install with one click on the 3 platforms that we support, which are Windows, Mac, and Linux. So Slicer can be used as an open source environment for software development. So you add your own software capabilities. But Slicer can also be used as an end user application because we make compiled versions of Slicer accessible that a non-computer scientist can just download and install on their machine. So you can have both ways. You can do development on Slicer, or you can use it as is. If you look at the current version of Slicer, and we have a method where on one hand we do a compilation every night, but then every about 6 months to 1 year we make what we call a stable release. The current stable release is Slicer 4.10, and if you look at Slicer 4.10, there are many modules with a lot of functionality, and there are extensions, some of them packages with multiple modules that are available through our App Store. If you look on the Slicer interface, this here is the App Store, and it basically accesses the extensions which are on a server at a company called Kitware. And basically, when you access the App Store, it tells you what is available. The extension manager will query the database and tell you what version of extensions are available for the version of Slicer that you are using at this point. Many people have decided to use Slicer as a platform to develop their own image analysis tools on top of Slicer. And here you see a partial listing of some of these projects that use Slicer as a platform to do algorithm research and make some of the algorithms available to the community. So for instance, there is the chest imaging platform and the Slicer heart extension package. And then of course we have the diffusion MRI extension package and a multi-tensor package that is called UKF, which stands for Uncentered Kalman Filter, which is a multi-tensor model that allows you to extract sophisticated streamlined data from if you have the proper acquisitions. We also make available tutorials so that you can basically teach yourself how to use Slicer and the different extensions. So it's not just the software, but it's the software, different extensions for specialized functionality, and then tutorials and sample data sets where you can learn how to use these capabilities in order to enable you to do whatever you need to do with Slicer. It turns out that Slicer is very popular. What you see here is a screenshot that I took today from the Slicer website, and you see the URL down here. When you go to this URL, you will see a live version of this, of what I'm showing you here as a static image. And so you see, if you look at the curve at the bottom, we see that we have every year an increase in the number of downloads of the compiled version of Slicer. And you see also that we have kind of these fluctuations where during the week we have more downloads, on the weekends we have less downloads. Also over the holidays, so Christmas and New Year's, we typically see dips in the number of downloads. But the overall trend is clearly increasing. We see regularly more than 400 downloads a day for the compiled versions. We make compiled versions available for Linux, for the Mac, and for Windows. And as you see, about 70% of the downloads are for the Windows version of Slicer. So, as you can imagine, it's not entirely trivial to make such a software platform and to make it actually work consistently over years. It requires a lot of effort. Slicer is built on I like to call it an ecosystem with a variety of building blocks, several toolkits like the visualization toolkit, VTK, the image analysis toolkit, ITK, and a number of other toolkits. We are using Qt, Python is available, and then there is engineering infrastructure to do the compilation, because as you can imagine, if you have so many different libraries and you want to make everything work on several platforms, you need to have ways to do the compilations and keep track of all the switches that you had to use to make things work on the individual platforms. CMake and CTest and CDash are tools that support the engineers that do this part of the work. And then we make Slicer available through a variety of distribution mechanisms and extensions as well. Slicer source code is available through GitHub, which is a modern version control system. So if you're a programmer, you can basically check out the version of the software and begin developing. And again, we have tutorials and how-to guidelines on how to do this. The software engineering process works in the following way, that we basically, a software developer makes a change to source code that gets then automatically every night compiled. We have a portfolio of automated tests that test whether the functionality of Slicer is maintained. So if I check in code and my code is not good, it might break somebody else's code. So if that code is being tested as part of the nightly build, then we will know that I broke the code and we can basically figure out what happened. So Slicer basically has over 600 automated tests that are run every time Slicer is compiled as part of this quality assurance system. And that is very important in order to maintain a stable version of Slicer, that when you download it, it will work as advertised. But again, we are not advertising it as a clinical tool, just to make sure. The core engineering team consists of people at Queen's University in Canada, at Brigham and Women's Hospital and MIT in Boston, and at Kitware in Chapel Hill in North Carolina. Those are the core engineers that maintain the platform, that work on upgrading the toolkit. So if ITK basically goes to a different version, then we will need to change and upgrade the ITK version that Slicer is using, and that requires a lot of work. So one of the applications that is important, I believe, to this community is image-guided therapy, where you're using imaging, preoperative and intraoperative imaging, in order to provide additional information. The underlying issues are relatively straightforward. So if you look at radiologists see the entire volume. So you see inside the structures. Here I have an example of a patient with a meningioma, a huge meningioma that is basically encased the carotid artery. The meningioma became basically manifested when the patient had some vision problems. Then she went to the doctor, and when they did MRI, that's what you see. So this is now a coronal T2-weighted image. You see here is the meningioma, this is the carotid artery, and what you see here is actually the chiasm that has been pushed aside. And as you know, meningiomas grow very slowly, and so you can get to fairly significant distortions when this type of things happen, until you have symptoms, until the patient had symptoms. Now, in surgery, of course, that's not what you see. This is the same patient. Now, a lateral axis, the temporal lobe and the frontal lobe have been pushed aside, and we see here the surface of this meningioma. Now, where is the carotid artery inside the meningioma? You don't see it in this picture, but you can see it easily on the radiology images, and that's what we are trying to do: take the information available in these volumetric images and make them available to help during the procedure. So in this case, this was my friend Aryan Abavi who did the surgery, and here you see towards the end of the resection the carotid artery, you see the optic nerves and the overall situation. And of course, this is a showcase, so the patient has no remnant symptoms after the surgery and was very happy about the results. So what does it take technically? One of the issues that we were interested early on, and what you see on the left is me being the experimental subject. I had an MRI done. We did a segmentation of the brain. And then we used a primitive setup with a video camera aimed at me, a video mixer that mixed the signal from the graphics board that had the 3D of the brain and 3D of the skin, and then manually did the registration between the two images, and that's what you see here. So you see my video image, and I was still wearing glasses like today. And then we used alpha blending with the color white to basically show the brain surface under the skin. And here you see some of the 3D of the skin on the sleeve of my collaborator, Harvey Klein, as he was showing the example concept. Now, notice that this was done in 1989, so quite a while ago. Today, of course, we have AR headsets and we have a lot of technology. It's essentially a commodity technology to some extent today. But that was 1989 when it was still kind of very bleeding edge. We also worked on navigation systems using optical tracking, and what you see on the right side is Tina Kapoor and Nobi Hatta, two longtime associates of mine, in front of our first navigation system, a home-built navigation system out of a collaboration with Eric Grimson at MIT. And so you see the workstation contained here the Sun workstation. Then you see the cart. It was built from massive steel elements, so it was very heavy. And the reason was that we decided to have a boom for the optical system. And this boom could be extended to over 3 meters, which means we could put the workstation away from the surgeon and the anesthesiologist, out of the way, and use the boom to reach the optical tracking system above the patient. We did a series of over 200 cases using this basic environment, and the level of quality of recording, so we used the skin surface to do the registration, and then afterwards, what you see on the left side, this is a volunteer subject. Her head is being tracked with these optical LEDs, and here you see a pointer. What you see on this image is the pointer, but now you see a virtual extension going inside, kind of extending the length of the pointer. And because we had the registration, we were able to basically align these two images. This overall setup was used in a very small series of procedures. So first we did the training with phantoms, then with volunteers, just to see if the alignment was working. And then finally we went on to do a series with actual patients who actually had brain tumors and underwent surgery. And among other, we didn't, of course, publish into the scientific literature, but in addition, we had also an article in the Scientific American in 1999 on the topic. And so augmented reality kind of, we were not the first, but we were early adopters of this technology. So we have this very long history that we started late 80s, early 90s. We were the first, or one of the first sites to have an intraoperative MRI, and this particular design with the vertical opening double donut was actually developed by General Electric company based on the vision of my mentor Frank Gilles. And then since then, so since the early 90s, we have been doing procedures using image-guided interventions as the target. The double donut was used for about 1,000 brain surgery or brain procedures, I have to say, because it included also biopsies. And then another 1,000 procedures that included other areas of the body. And that's one difference between the MR-guided intervention effort at the Brigham and Women's Hospital and many other locations, that the effort is not limited to one specialty, but we have multiple medical specialties present and active in the environment. I think this is a very important distinction. Of course, it requires more resources, but on the other hand, it makes it easier to have cross-fertilization. Something that was developed to enable prostate procedures can be used in brain procedures and vice versa. And we have seen this type of technological cross-fertilization over and over again over the years. In 2011, the second generation interventional environment was ready to start operation. This is an environment that is based on the experience in the previous decades. Basically, we have a setup where we have a suite with an operating room, a ceiling-mounted image system similar to what you have in Beijing, and a PET-CT. The MR system is a 3 Tesla system. There is also here a C-arm that can be used for cone beam. We have, of course, a variety of different navigation systems. There is a cyclotron in the hospital, so we can use not just FDG, but other substances as well. And then you have the entire suite where you have the control rooms, and you have here facilities, soil facilities, and all the other things that you need in an operating room environment in order to be able to function properly. One of the distinctions that we have learned to work with is that we use commercial products, and wherever possible we use commercial products. And we move on to the research environment only when we need to do things that the commercial products cannot do. So here on the right side you see 3D Slicer and BrainLab working side by side, and we worked with BrainLab to be able to export the tracker system into Slicer, so that what you see now, we were able to do interactive tractography. This little red sphere is the tip of the pointer, and so we can look at the white matter tracts that's extracted from single tensor tractography to help in making surgical decisions. Again, as a clinical research under an IRB. In order to do this, we need a slicer not just to be able to display 3D, but to be able to talk to devices. We are using an open source protocol for this that we originally developed, that we call OpenIGT-Link. And here you see a technology demo where the accelerometer in a phone is being used to define a scan plane in the MR scanner. And what you see on the display here are basically single slices of a spherical water phantom that is inside the MRI scanner. And as the scientist Junichi Tokuda is changing the position of the telephone, the scan plane definition gets changed. You see on the left side here, basically the block chart, how this entire system is set up. So you have the smartphone that talks through a Wi-Fi router, an OpenIGT-Link to the MRI computer, which in turn basically initiates the scans. Same approach, but here it's now ultrasound, tracked ultrasound. We have an electromagnetic tracking system. This is the sensor attached to the ultrasound head. This is a prostate phantom. And so you see now that the ultrasound being tracked and the actual ultrasound image being fed into a 3D display inside Slicer. So OpenIGT Link allows us to interface to a variety of different devices, and then we have this Plus library that allows the streaming of the ultrasound images into Slicer. The initial technical work was again done around 2011. So where are we today? If you look at the Amigo environment, we have done over 2,000 procedures in that environment. As you can see, brain tumor resection, deep brain stimulation, and a variety of other procedures in the brain, but also a smaller number of procedures elsewhere, breast surgery, endocrine surgery, radiation oncology, in particular brachytherapy, both in OBGYN and in urology, and then finally biopsies in a variety of different locations. So today, Slicer can be used to enable research. As I'm sure Dr. Chen will tell you, it can be interfaced to both AR and VR capabilities in addition to many other things. Now, I would like to talk very briefly, only for a few minutes, about some of the things that are going on in the background. One is that for imaging, there is an increasing reliance on DICOM. If you go back 20 years ago, we got the images from the scanner, we removed the header, and then we did the work. Now, increasingly, we are working to be able to have native support, high-quality support for DICOM. DICOM is important because potentially, and we are doing it now in research mode, you can basically take the results of your processing, the segmentations and 3D models, and basically store them into a DICOM format, which means that you can keep them with your original data, at least in the research environment. And I think the importance of being able to keep annotations, the results of segmentation and registration, together with the original data, will increase as we use more and more of these technologies. So that's one push. We have been pushing DICOM for at least 6-7 years, and there is a lot of working DICOM today already, but we are not yet quite at the point where everything works the way we would like it to work, but we will get there. This is a long, sustained strategic effort to improve Slicer. The other effort that is going on, and I'm showing you here only 2 still images, but you can go to those 2 URLs that you see here, ohif.org and openanatomy.org, to basically look at it for yourself if the firewall will let you. We have been, again, for several years prototyping with modern technology, web-based technologies, such as JavaScript and WebGL, and we have first promising results. These are programs. The advantage of this technology is that you don't need to download and install the software. It happens when you just point to the URL. It will basically download itself and install itself. That has huge advantages. Today, these type of approaches are somewhat limited in how big of a memory footprint you can have, and your performance limited. So it's not quite ready for prime time, but the initial results are very promising. So again, 3D Slicer is a community-based effort, and it's an open community. We welcome anybody who wants to participate in the community. One of the vehicles that we use to make the community work, in addition to forum software, mailing lists, and video conferences, are in-person conferences that we organize roughly every 6 months. And we have been doing this for quite a while. And so the next project week is in 2 weeks in Boston, or 3 weeks. And then we will have one in January on the Canary Islands of Spain, so in Europe. And again, if you're a developer and you're interested, you're welcome to join. And with this, I believe I've reached the end of my presentation. I hope that you enjoyed it and that it was useful. And I'll go out of the slide presentation mode. And I think we lost the connection with Dr. Chen. So let me try to call him so that we can get to the next stage of it.
Great.
Hello?
Hello, can you hear me?
Yes.
Okay, great presentation. So on the mobile phone side, there's a delay about 20 seconds. So maximally we have 2,500 audiences who have already enjoyed the show. So now I'm trying to answer some questions from the audience. Let's see. 好，大家可能听到吧？这个刚才的这个演讲很精彩啊。那么我们现在再看看观众的问题啊。有我这儿比较慢，我在替他翻这个问题。有没有人现在吧开始提问吧？这个打字或者英文、中文都行。前面有没有人提问的？这个我这儿操纵的很慢。我现在在中国去操纵在德国的一部电脑啊，然后再看这个前面有没有提问题。好像前面好像没有人提问题哈。现在我先把这个窗口啊给拉大，让大家看一下这个大神的这个照片啊。好，有人说今天英文讲课有难度，这个有没有人提问？现在大家都那么乖啊，为什么没有人说话？没有题吗？So here's a special audience who sits just beside me, and he want to give some comments for today's presentation. So please, Dr. Tang.
Thank you, Professor. Kikinis, thank you very much for a great presentation.
It's quite a pleasure.
So here's Dr. Yang also, who also is now in Germany. He's a PhD student in University of Marburg. Whose mentor is Professor Christopher Linsky. And Dr. Yang asked, I believe you have already seen the question, right? As a beginner in neuroimaging analysis, a problem about the data format bothers me a lot. Normally, the academic platforms like 3D Slicer can process the data in DICOM, nifty or NRD format, but commercial, where's that? But commercial platforms, which is always used in the clinical settings, accept only the DICOM data. What if I need to do some pre-processing in academic platforms and transfer it into the commercial platform? Is there any plugin in 3D Slicer to convert nifty or NRD data into the DICOM data?
Yeah. So that's a good question, and that basically touches on the topic that I mentioned towards the end of my presentation, which is DICOM. The neuroimaging community basically adopted non-DICOM standards, which is in particular nifty, because at the time when that work was done, DICOM did not provide the necessary capability. DICOM has evolved in the last 20 years tremendously. Today, there is support for segmentation objects, and there is support for other types of annotation. And so the answer is that you need to get the results of your segmentation into DICOM format. If you do it inside Slicer, this is possible in research mode. If you do, for instance, on the other hand, if you do a diffusion tensor imaging, the results of the processing are tensor stream flows. And those data formats there is right now active work going on to make a DICOM version of that data. And actually, Lauren O'Donnell, who is a scientist at the SPL in Boston, is working with BrainLab on compatibility, interoperability, so that with the objective of being able to write tractography results in a format that can be imported into the BrainLab system, using DICOM format. So right now it's possible in a collaboration setting with the vendors. It's not something that works out of the box.
Okay. May I?
Yes, please.
Could you please just give me several minutes to interpret this?
Yes,
That's
yes.
a lot of information. 刚才呢是德国马布大学的杨佳博士啊，刚才问了个很好的问题，就是说这个在用 Slicer 的时候呢，通常我们需要的数据的格式是这个，比如说 NRD 格式，比如说 nifty 这个格式等等啊。那么问题是一些商业化的导航和影像处理的平台呢，经常用的是通用的 DICOM 格式。那这个Slicer 怎么样也能够转换这个使用这个 DICOM 这个格式呢？这个是个问题啊，这个确实我们也平时深受这个困扰啊。那么根据教授的这个回答呢，就简而言之就是说这个目前来说啊，这个要达到这个格式的这个完全通用是比较困难的。在 Slicer 的这个开发版本和这个 research mode 这个研究版本当中呢，是可以有一部分这个nifty 的这个格式或者是 DICOM 格式可以变成 nifty 的，或者是就是互相这个转换了。但是呢，总体来说呢，还是直接使用 DICOM 的格式呢，还是有困难。第二个呢，就是 DPI 的一些处理的这个结果呢，目前呢有人正在做啊，这个是这个也是 SPL 实验室的一个美女教授啊，我这个跟我很熟，她在进行这方面的工作，但总体来说呢，暂时还不行，还不能够直接的使用啊。Okay, there are several other questions. One question, actually there are two questions which is similar. One is, how can we integrate the DSA data or ultrasound data, which is not tomographic data, which is like rotating DSA angiography data or ultrasound data into this kind of integrate this kind of data into slicer and to do the processing. Is that possible?
Yeah, so in DSA, if you have single projections, they don't really integrate well into the 3D coordinate environment that you have in slicer functional, because it's basically a projection. And so you could import a single DSA and put it geometrically where the plane was, but it's not going to be integrated the way you would like to do it.
Yes.
If you do a rotational CT with your DSA, then you have a volume that in principle you can fully integrate.
We have already tested this kind of rotating, which is called three-dimensional DSA, but unless we reconstructed the data into a tomographic data, we cannot integrate.
So again, it's not the computer science capability of importing a DSA. It's the philosophy. What is a DSA? A DSA is a projection image, and it is basically the sensor, the detector, is outside of the patient. So you can make a representation where you show the DSA where the patient is relative to the patient data, but it's not going to be what I believe the person asking the question really would like to have.
Okay, I see. Then how about the ultrasound data?
Ultrasound data, so we have an active research activity going on using ultrasound in neurosurgery. We have a computer scientist, Sarah Frisken, who is funded to do work along those lines. So the individual, if you have a neurosurgical ultrasound, it's usually a 2D. But if you do tracking of the ultrasound transducer, you can get a volume. And the experience is that you have to be very slow in moving the transducer while you are acquiring the volume. Then you can get a reasonably good quality volume from tracked to the ultrasound and use this to do intraoperative registration.
Okay, great. So please allow me to do the operation. 刚才呢，就是问的是大家问的两个问题，这两个问题实际上是类似啊，就是说DSA 的数据还有超声低超的数据能不能用 slicer 处理，对吧？这个 DSA 呢，就是这样 ，DSA 呢，如果是一个标准的，就是说标准的单方向的投射的 DSA 数据呢，那么是不能导入slicer， 因为它只是在一个层面上的一个透射的数据，对吧？那么这是不行的。但是呢，如果一个旋转型的所谓的3D DSA 的数据，那实际上是管球啊在旋转了一圈以后采集的数据，这个呢是能够导入的啊。这个呢，我们自己在我们的301测试的方法呢实际上是一个变通方法，就是说把这个3D DSA 的数据呢，它只要是能做3D DSA 的都能够重建成一个类似 CT 的一个断层扫描数据，实际上它就相当于一个单排的 CT。那么这时候再把这个重建出来的这个 CT 的这个 volume， 这个卷这个断层扫描这个卷导入slicer，这是完全没有问题的，这是可以的啊。那么好，然后呢，另外就是超声这个目前还不行啊，但是有一个小组正在做这方面的研究啊，就是也是 SPR 实验室的，正在做这方面的研究，主要是 希望能够追踪这个 B 超的 introducer 这个探头啊，然后再来重建这个各个方向的图像。但是因为本身来说 B 超呢，它是一个2维的图像，原则上来讲它是目前是无法导入这个 slicer。好，那么下面还有一个问题啊。So the next question, someone asked that is that possible to host one project week in China?
Yes, but anything is possible. But again, remember I said that Slicer is based on a community process. Mm-hmm. The community is open to anybody to participate. But unless you participate, you're not part of the community. If I look at the Chinese participation in the project weeks, we don't have a lot of Chinese participants that come from China.
Yes, that's mainly because of the expense.
I think it's twofold. On one hand, because of the expense, and of course, if we were to do a project week in China, the same would be true for the Americans and the Europeans. And the second one is the language barrier.
Yes.
Your English is significantly better than my non-existing Chinese. But if we were to do a project week in China, where I agree with you, the majority of participants would be Chinese, it would not be very attractive for people from outside of China because of that language barrier. And as I say, it's a symmetry. I mean, I understand what you're saying. I understand this. And so you have to keep this in mind when we have this conversation. One answer would be to say, yeah, let's do a Chinese version of Project Week in China, in Chinese. And that's possible in principle. But again, so for instance, the one in the Canary Islands, the driver is a professor, a senior professor of computer science at the University on the Canary Island, and he attended the project weeks for several years until he understood how they are working. And then basically he said, I'm interested to do one. And at that point we knew him well enough that we felt comfortable working with him. So the answer is, it's possible. There is a certain process that we would have to work through, if there is interest. And it will require local commitments. Whoever wants to organize it will need to figure out how to fund the effort. Sorry for the long answer.
这回答很长啊。就是有人问啊，能不能在国内办这个 Slicer 叫 Project Week， 它就是在这个一些研发的项目的讨论啊、计划啊等等，在这个中国，但是目前来说还是有很多的困难啊。还有这个KikiNis教授也讲了很多。那么我认为呢，他说以前的这个 Project Week 很少有国内的同志去参加。那么我说这个可能跟他也是开个玩笑，就是说这个主要是费用问题了。那实际上咱们中国还涉及到，比如说签证问题啦，比如说这个钱确实也是个问题啊。然后他说呢，还有这个语言的问题啊，还有这个，实际上我个人谈谈我加一个因素啊，就是说咱们在国内呢搞计算机科学的这些同志们啊，跟医生离得太远，就是我们的医生啊跟搞计算机科学的人结合的不紧密，所以呢这方面呢一定要是大家合作起来才有这个前景。所以总体来说是不大可能这个在中国办这个 Project Week。好，那么 Okay, now next is still Dr. Yang from Marvel. She asked that, did you see the question, is there any module or extension for fully automatic segmentation of brain tumor right now in slicer?
Fully automated, no. So the short answer, not fully automated.
Okay.
But the newest version of Slicer has a new version of the interactive segmentation. So if you go back 10 years or 20 years, we had the editor in Slicer. Based on the experience in the editor, we, as a group in Queen's University in Canada, completely rewrote the editor. So this was two professional programmers for 3 years. So this was a tremendous amount of work. The new infrastructure is called the segment editor. The segment editor has a number of half-automated and semi-automated algorithms available to support segmentation. And that's the best technology that we have available, and I believe many other people have available for brain tumor segmentation. In particular, there is a very fast version of an algorithm called GrowCut that is available in the segment editor.
Okay, thank you. 这儿还有一个同志啊问说，之前看过关于3D Slicer 的报道，可以把肝脏 CT 的数据与彩超数据融合，在彩超下引导肝脏参测。教授能把这些操作的具体流程，还有我开展这方面工作需要添加设备说一下吗？我觉得是这样，给这个同志提个小意见啊。你这个既然看过报道的话，如果是正规的学术论文，那么建议你呢把这个论文啊好好读一读，它里面肯定有方法，肯定有这个方法，因为科技论文嘛，它就是为了要能重复的。所以呢，这个像这种这么复杂的这个技术问题，在这儿问呢，我觉得是不太合适。当然我可以帮你问一下，但是我觉得这个会占用太多的时间。有文章你自己去看。另外说要提供一个具体的病例，这个有点过分啊，这个有点过了。大家提问题别的问题，好吧？There's a guy who have already read one article about the using 3D Slicer software to do the co-registration of the CT data and the ultrasound B data for in the case of the hepatic tumor or lesion, and then do the lesion biopsy, needle biopsy, with the guidance of the ultrasound B. So do you know? Can you offer any technical details or information for this technique?
So I'm not familiar exactly with this particular paper, which shouldn't surprise you that by now there are over 8,000 papers published in Medline that mention Slicer. So I'm not familiar with all of them. But in general, I would think that for CT you would have to have post-contrast. And it might make more sense to use MRI of the liver to do this co-registration.
OK. 这个跟我刚才的这个预测的差不多啊。这个kikinis 教授没有看过这篇文章，他也不太知道你到底这个问题问的是里面涉及的东西到底是什么。确实你这样直接这样问啊，确实是这个没法回答。我建议你还是先仔细看一下这篇文章，然后再说啊。如果是正规的学术报道的话，那应该会有技术细节在这里面，好吧？那么下面还有一个是不应该问问题的人啊，这个是谢国强同志。谢国强同志刚刚从 SPR 实验室回来，为什么有问题不在那儿问，跑到这儿来问呢？对吧？那么，但是啊，为了表示公平，我们还是把谢国强同志这个问题问一下啊。这个叫他问题跑哪去了？稍等一下，我这上面我得到上面去看一下啊。是啊 ，yes. So there's a guy, there's a guy who just came back to China from your lab. He attended this webinar, and I want to ask a question. Is that possible to export the result of a volume rendering? Just a minute. I didn't see that. Just a minute. Is that possible to export the volume rendering models generated from slicer for the later 3D print, and extract? How can we extract the vessels out of the skull base? Actually, I guess you want to ask, how can we extract the vessels out of skull base?
So I think there are here multiple concepts that are being mixed, because volume rendering per se, you have these transfer functions, and so what you see is based on the transfer functions. 3D printers typically require actual surfaces. So what you really should do is actually use again the segment editor to segment the structures you're interested in, and if they are segmented, you can eventually save them in STL format, which is a start point for 3D printing.
Yeah, I agree. I guess actually, no, the problem with the surface rendering for like CT angle data or MR angle data will be the surface model is not as smooth as the model generated from the volume render. So that's maybe the reason why.
No, but you see, that's the point. Volume rendering does not create a model. It just creates a visualization, and the view rays accumulate over the entire volume. So you don't have a structure so it doesn't fit the concept of 3D printing. Hello? I think I lost you. Do you want to try? Your Skype is frozen.
Okay, now.
Okay.
Now. Hello?
Yeah.
Can you hear me?
Yeah.
Okay, now we're back online again. So I will interpret this to the audience. 刚才呢是这个谢国强同志问了一个问题，就是说这个这也是一个常见问题，就是说用 volume rendering 用容积重建出来的模型能不能输出作为 3D 打印，或者说是另外第二个问题，实际上就是如何去把这个容积重建的模型，我猜想它意思是指在做血管的 volume rendering 容积重建的时候，把这个血管从这个颅底的骨头上剥离出来，分离出来。那么这个教授的回答是这样的啊，就是 volume rendering 它本身啊是不是表面重建，容积重建跟表面重建的概念，大家有空再去自己上网去查一查，到底什么叫 volume rendering， 什么叫 surface rendering。那么这个 volume rendering 呢，这容积重建呢，它是没有表面，没有表面的话呢，不生成这个表面的话呢，那就无法去输出到3D 打印。所以呢，如果你想做3D 打印，那就要做 surface rendering， 然后再把这个文件存成一个 STL 文件，再去做3D 打印。那么所以这个问题两个回答都是不行啊，目前用 volume rendering 不行啊，不能这样。然后还有张华平同志问了一个问题啊，就是说这个问题也很好啊，Rob, hello.
Yeah.
another question, which is, in the case of acoustic neuronoma, is it possible to use the slicer and the DTI-based fiber tracking to display or depict the pathway of the facial nerve?
In principle, yes, if your scanner is very good. So the limiting factor is not 3D slicer per se, but the resolution of your DTI data.
I agree.
We've had an ENT doctor work on this topic, and he's right now working to writing a paper on the topic. But ultimately, it's really a question of the resolution of the DTI.
The next question is, can we display the vessels here, either arterial wing with diameter less than 1 millimeter?
So again, it depends on the resolution of your MR angiogram. If you have good enough resolution, in principle, yes. A slicer has support for so-called oversampling, so that you can artificially increase the number of voxels, and that can help in the segmentation of fine structures. But ultimately, if it's not in your data, then it's not in your data.
OK， 这刚才呢就是张华平同志问的这个问题啊，就是说这个在这个用 slicer 和 DTI， 他没说 DTI， 我帮他补的，用 DTI 和 slicer 能不能显像这个面神经？另外呢，在 CTA 的这个成像的时候，如何能够显像1毫米以下的动静脉和血管？那么这个这位教授的回答是这样，就是说这个我也同意啊，就是这个主要不是软件的问题，主要是在于你提供的原始数据，就是你的扫描方式能不能提供更高分辨率的影像啊？这个DTI 呢，这个我们团队是有发表过文章的，在 Journal of Neurosurgery 上是可以的啊，可以，但是对数据的质量要求是比较高，它不是每一个都能成功，有一定的成功率，但是技术上是完全可行的。那么至于说血管，张华平同志问说1毫米直径1毫米以下的血管能否成像？实际上是这样，我们首先要澄清，就是这个Kikinis教授的回答还是说要看你的数据的质量，对吧？那么我补充一点啊，就是因为这个具体呢，你可以看看我们在去年5月份发表在 World Neurosurgery 上的这篇文章，讲到我们用 slicer 怎么样去进行虚拟现实的重建，去描绘这个后颅窝血管神经压迫的情况啊。那么这个里面呢，实际上对于小口径的血管，实际上因为在 MRA 上面 ，MR 这个血管动脉成像上面，它探测的不是血管口径，而是流速，它是用多普勒效应这个探测的啊。那么它是探测流速，当然在这儿越细的血管，它可能流速会越慢，所以越难探测。那么你要想提高检出率，提高这个数据的质量，另外呢 ，slicer 做的重建要漂亮，你就要怎么办呢？要用更高强长的机械啊。我们是最高用到7个 Tesla， 7个 T 的机器去做，那么这个血管成像明显是比1.5或者3T 的机器要好得多。所以我相信啊，这个基本上原理来说，你要想解决你这个华平同志问的这个问题，基本上来说，总体原则应该是提高原始数据的成像质量。那么提高原始数据的成像质量，在近期内，我相信在主要的手段就是提高强长，用更高强长的机器去进行扫描啊。好，那么下面一个问题是来自于徐清华博士啊，就是excuse me, Rob, Dr. Xu from my team raised one question: Is it possible to train slicer to segment lesions automatically with machine learning or deep learning?
So right now there is some research work going on in deep learning, not in segmentation of brain tumors, but on other topics. We've been working in parallel to make the deep learning engines that are publicly available more accessible from inside Slicer. And in the most recent version of Slicer, that's the case. But right now, at least in the SPL, there is no effort going on to do segmentation of brain tumors per se. One of the reasons is that most of the deep learning algorithms need large number of training data sets, which are fully segmented in large number. And that's very difficult to achieve in neurosurgery. Getting large numbers of consistently acquired data sets that have been fully segmented. And because of this, in principle it's possible, but right now nothing is available.
Yes, I agree. Dr. Xu suggested that is that possible in the future to predict whether there was a gene mutation through machine learning with Slicer? I mean,
yeah.
I guess he mainly means the IDH1 gene genetic mutation.
Yeah. So again, this is a research topic. I have a collaboration with a scientist by name of Hugo Ertz. And Hugo is working on radiomics. And the first generation of radiomics was using a conventional pattern recognition algorithm. Right now, state of the art is to use machine learning, deep learning, to do the radiomics-based distinction. Hugo has, among other things, worked on doing radiomics research in brain tumor data sets. So there is some research going on, there is some work going on to make some of these tools, the first generation radiomic tools, are available as a package which is called PyRadiomics and which is interfaced to Slicer. The machine learning based algorithms, they are currently working on the engineering to turn the research tools into tools that can be distributed. So it will be coming, but it's not available today.
Okay. 刚才是徐新华博士问了一个很好的问题，就是说有没有可能性通过这个机器学习或者是深度学习啊，就和 AI 了，然后让Slicer 能够自动的进行这个病变的分割，那么或者说是来预测某一个病变有没有基因的突变。那么目前来说，我个人补充的就是说，目前研究的比较多是 IDH1 的这个突变与否的这个突变型的预测。那么 Kikinis 教授的回答是这样，就是说理论上来讲，用 Slicer 整合这个 machine learning， 整合机器学习或者深度学习的这个模块以后去做 segmentation， 这都是可以的啊。但是而且他现在确实有团队正在做这方面的工作，但是不是针对肿瘤的，是针对其他病变的。那么问题就是在这方面呢，需要大量的训练数据、大量的训练这些数据和大量的时间，所以呢，目前呢这个工作正在做，还没有能够成熟。那么另外呢，这个后续的这个所谓影像组学啊，这个人工智能预测这方面这个模块呢，用机器学习的这个模块还在开发中，还没有整合进 Slicer， 所以暂时来讲，目前来说用的软件是不能够这样做的啊。OK， 还有没有什么其他的问题？好像是不是就这么多了
I think pretty soon, by the way, I will have to move on.
Okay.
But you know, as you know very well, I'll be in September in Beijing.
Yes.
So perhaps an opportunity to advertise for this.
Yes. 这个大家还有问题不要紧啊，就是在这个今年9月，就是今年9月7号、8号2天啊，就是在这个北京的世界神经外科大会之前，那么我们特邀了 Kikinis 教授到北京去授课，我们会办一个 Slicer 的培训班，到时候呢，大家欢迎到北京去当面跟Kikinis 教授求教啊，或者去膜拜也可以的啊。那么好，最后还有一个问题啊，就是
I think I lost you again.
Hi.
Hi. So I think
I'm back again. Here's the last question. As we know, so far we used with Slicer, we can only reconstruct the static image, a static 3D image. So how about the dynamic image? For example, the flow of the CSS fluid or the pressure gradients in the case of AVM, this kind of 4D image. Is it possible to process it with Slicer? Or, for example, the dynamic
So I think we got disconnected again.
So, hello?
Yeah, I hear you again.
Did you hear the last question about the 4D image?
Yeah, so the problem is 4D is not the same as 4D. And when you do analysis of 4D, you need to develop specialized processing depending on what kind of 4D work you want to do. So there is capabilities in Slicer for dynamic contrast enhancement using the Tofts model. There are models for this. There is also another one for arterial spin labeling. So depending on what kind of dynamic data you want and what kind of analysis you want, you have to develop a customized version.
Okay. But the major question is, how can we develop this customized model? Or can we only hire some team of the computer engineers or programmers to develop this kind of extension?
Yeah, if it's not available in Slicer today, you can develop yourself or work with somebody to develop it. Remember or keep in mind that doing this kind of collaboration requires cross-training. So the surgeons need to learn some of the concepts in the image processing, and the computer scientists need to learn some of the concepts of the surgeons, and that takes time. So you cannot just hire a programmer through advertisement and expect results in a few months. Typically, these type of projects are multi-year projects, and there is always a training phase at the beginning where things are moving very slowly.
Okay, thank you so much. I believe, I think today's webinar is a complete success. So thank you for your time, and hopefully we will have more community members who can discuss this details with you in this September. Okay?
Yeah. So thanks for listening to me, and I'm looking forward to my visit and to interact with the Chinese community.
对。那行，因为这个 Kikinis 教授上面还有工作安排啊，所以这个就今天的转播这个直播就到此结束啊。因为还像我们说的样，9月份他就来，他刚才也说了，很期待9月份能到北京来跟大家见面啊。到时候你有什么问题可以当面跟他再请教，好吧？那么下面我们就感谢这个 Kikinis 教授，并且结束我们今天的直播。下周二依然有这个 TNT 大讲堂啊，这个内容一样精彩啊，欢迎大家继续关注。好，谢谢各位，我是来自301医院的陈医生啊，再见。